At the end of the lesson, you are expected to define the properties of directed graphical model, compute conditional probabilities using Bayes' theorem, and appreciate the significance of directed graphical model. Let's begin by defining the properties of directed graphical models. So a directed model, which is defined on X, is specified by two properties. So let's have the first property, a directed acyclic graph G, or we call it DAG for short. It has nodes element denoting element xi of X. So maybe at this point you would like to ask me, okay, Joseph, what is the meaning of directed acyclic graph? So for better understanding, let's have this illustration. So as you could see here, we have 1, 2, 3, 4, 5. So 5 nodes. And these 5 nodes are connected by different edges. Okay, so as you can see, there is no defined sequence of movement of the arrows. So for this node, it is connected to this one. This is connected to this with an arrow, right? And also with this one going to this one. And this to this, and this one to this. So as you could see, there is no pattern, obvious pattern that can tell us that there is really a cycle. Okay, so in short, there is no directed cycle, so we cannot follow a sequence of edges. So I think I have given you already what this directed acyclic graph really means. So if you have some questions, just write down below in the comments so we could discuss properly. Then we have number 2 property. So it is also a set of local conditional probability distributions. So we have P xi, given that the parent xi. So with P a g xi. So with this the parent nodes of xi in G. So also it factorizes the joint distribution of the node variables as this statement describes. So in our last lesson, lesson 14, we learned about this factorization, and then we learned how the different nodes can be factored depending on the kind of connections they show. Okay, so the link is given in the description below, and I suggest you study it for better understanding of the lesson. Okay, so these graphical models are also known as Bayesian networks. Let me write that. I am sure it is not your first time hearing this concept. Okay, so as you could see in this concept, Bayesian concept, your understanding of conditional probabilities, and joint probabilities are really very important. So I suggest you study. So again, the link is given in the description below. Okay, so for better understanding, we need to have a concrete example. So let's take note that a directed acyclic graph has no directed cycles. So variables can be positively dependent. It can also be negatively dependent or unrelated. So for example, let's have this illustration. So we have here 3 nodes or 3 variables. We have sprinkler, we have the rain, then we have the wet grass. So what's the meaning of this? Okay, so what is the story behind this? So it's like this. If it rains, there is a lesser chance of turning on your automatic sprinkler. Okay, so the next day in the morning, if you see that the grass is wet, it is because it has rained, or it is because the sprinkler does its job. Okay, so using the graphical model, we can say that P, we have this one, P, or the probability of RSW. So R means rain, S means sprinkler, and W means wet grass. Okay, so we have the probability of R S W is equal to the probability of R, then we have the probability of S given R, and the probability of W given S and then R. So in Bayesian network, we join nodes or variables that have a directed link to demonstrate dependency. So what are the links here that demonstrate dependency? So wet grass, from sprinkler going to the wet grass, then from rain going to the wet grass. Look at the arrow. Okay, and also from rain going to the sprinkler, but in this case it says here it's negatively dependent, which describes the relationship between sprinkler and rain, and from rain to wet grass, and also for sprinkler and then wet grass, because they have the same direction of the arrow, it says here that it's positively dependent. So what do you mean by this? So in this example, having a wet grass in the morning is dependent on either raining or turning the sprinkler on. So as you can see, there is a negative dependence between rain and sprinkler, because turning on the sprinkler depends on the chance of raining. So there can be no relation in case when even if it rains, you still turn it on. Okay. So at this point, it is significant to mention that joint probability and its expansion to chain rule is very useful. So however, this makes the situation more complex. So this is why we use Bayesian network to simplify everything. So for example, instead of using P, S, okay, S, R, and W, where S, R, the probability of S given rain and then wet grass. So we can use, instead of this one, we can use P, S given R, because it is independent on W. So which one is independent? As you could see, we could use again P, S, S, R, and then we have omitted W because sprinkler is independent on W. Okay, so W here, wet grass, does not have any connection as to the chance of turning on the sprinkler. Okay, but it's actually the other way around. It is the sprinkler that has a direct connection to the chance of having wet grass. Okay, so let's have this table for better understanding of what we mean by this. Okay, so this table shows the conditional probabilities of different events. So for example, we have rain. Okay, so if it's really going to rain, then the probability of having a rain is 0.3, and the one that is not raining is 0.7. So on here we could see here the probability of S given rain. So if it's true, then it's 0.4. If rain is false, then it is 0.4 if S is true. If rain is F and then S is false or F, then it's 0.6. Okay, so rain is true and then S is true, is 0.02. So rain is true, S is F, it's 0.98. So this will remember joint probabilities. So actually this is our our past lessons. So here we could see a more complicated, because here we have W, which is connected to S and then R. So when the S is F or false, and R is false, then it is 0.0 if W is true, but when it is false, then it is 1.0. Okay, so also for the rest. Okay, so I leave that one to you to read for 1, 2, 3 for the 3 situations for both true and false. So we're going to use these values to compute for the different situations. Okay, so using these values we can make some predictions. So let's find the conditional probability of P, which is equal to let's find the conditional probability of W, which is equal to T, S is equal to T, R is equal to T. So what we're looking for here is everything is really true. So we have the probability of W, which is equal to true, or T, given that S is equal to T. Then we times the probability of S, given that S, which is equal to T, given that R is equal to true, or T, and times with the probability that R is equal to T. So where did we find 0.99 for our first probability? So it is here, this one, when S is true and then R is true, W is true, it's true, and then it's true, S is true, and W is true, so it is 0.99. Okay, that's why it's 0.99 here. Then 0.02, S equals T and R is equal to T. So R is equal to T and S is equal to T. Okay, so we have here, and then we got 0.3 for R is equal to 3. So multiplying them, then we have 0.00594. So it means that we have a 0.00594 chance of having W is equal to T, S is equal to T, R is equal to T. So in this case, actually what we use here is the Bayes theorem followed by the respective marginal probabilities of the different situations. What is this for? Why do we have to study this? It has a great ability to describe structure in data in terms of easily understandable representations. It is also significant for Naive Bayes, hidden Markov model, restrictive Boltzmann machine, and neural networks. After all being said and done, let's try this. What are the properties of directed graphical model? And using the same table in our discussion, find the probability that W is equal to F, S is equal to F, and R is equal to T. Please write your answers in the comment below so we could discuss properly and others too can see your answers, so there would be very rich interactions between and among us. Do not forget to subscribe, like, and share. Please click the bell button to be notified every time we have a new session. See you in the next lesson.